Welcome to Lyons Township High School AP Physics. Today we've got an example involving Newton's second law and a block on a ramp with friction. Okay, so let me kind of explain the situation, and you may want to pause the video here and draw and write this stuff down. So I would suggest you do that real quick. All right, so got a ramp. Okay, you got a block you're pushing with a force P, which I'll explain in a second. But you're pushing on the block, that's you. Okay, you're going to push the block for a distance x, and at that point, it's going to be moving, and then we're going to let it go. All right, and it's going to continue coasting up the hill and eventually stop. All right, so the push that we're going to push with, the wording is going to be as follows. It'll say something like, you push with a force that's equal to twice the block's weight. Okay, so not another way of the block, it says M, that's mass, and it doesn't give me a number. Okay, but if I were to ask you what's the weight of the block, you would hopefully say the weight equals mg. Well, if I'm pushing with twice the weight, then what force is that? Well, that's going to equal 2 mg. Okay, so we're going to push with a force equal to twice the weight of the block. If I do that, if I make P some fraction of the weight of the block, then I don't have to give you M. It's going to cancel out. Okay, so there you go. All right, other data, we got the angle of the incline from the horizontal, we got the coefficient of sliding friction, and we're going to push for 3 seconds. So we're going to ask the following questions. At the end of that 3 seconds, that's here, okay, what is x, how far did it go, and what is the velocity at that moment? Okay, we'll call that v at 3 seconds. Okay, so we're going to find that, and then we're going to find, after I let it go, now it's moving, but it's going to stop. Okay, how far does it go before it stops? That's d. Okay, so we're going to find all three of those things. So it starts with, any problem that involves forces starts with, you guessed it, an FPD. And what we're going to do is we're going to draw two FPDs. The first one is what I call the College Board FPD. We're going to draw exactly which forces act in exactly which direction. And then we're going to split those forces up into components. We're going to draw a second FPD. That second FPD is going to be we're going to split all the forces into components that are either parallel to the motion or perpendicular to the motion. So, having said that, let's draw the College Board FPD. So, got my box, I'm pushing with a force P. Now notice that I always start at the dot and draw an arrow from the dot. So even though P is pushing on the box, it looks like a pull over here, but it's just drawing from the dot outward. The block has a weight, so that is mg. Okay, I told you there's friction. That's going to be against the motion, force of friction. And hopefully the ramp is holding it up, okay? Now the ramp is supplying a normal force. That normal force is perpendicular to the ramp, always perpendicular to the surface. So we've got Fn pointing that way. So those are the four forces acting on the block between here and here for that first 3 seconds, okay? Now we're going to split this up into components, okay? So we're going to split up the forces into components that are parallel to the motion and perpendicular to the motion. Okay. Now, having said that, you'll notice that 3 of the 4 forces are already parallel to or perpendicular to the motion, so we don't have to do anything with those. So I will recopy those right now, and I'll do this down here. So we've got Fn, we've got friction, we've got P. Okay. Now, mg, we got to split that up into pieces because mg doesn't point perpendicular nor parallel to the incline. There's a little bit of both, so we got to find the two components. Now, if you're at LT and you're in class, your teacher showed you how to do this. I'll just do a quick refresher. You've got a component of mg that's perpendicular to the incline and a component of mg that's parallel to the incline. There's a little right triangle for you. This angle here is congruent to that angle there. If you want the geometry, come on in and we'll show you that. But this angle and this angle are the same. So having said that, the perpendicular component to the incline, that's the adjacent leg in that little right triangle to this hypotenuse, so that's cosine. So the perpendicular component of weight to the incline is mg cosine theta, and then the little parallel component of mg to the incline, that's the opposite leg, that is mg sine of theta, okay? And I told you guys that we're pushing this block up the incline, so we're going to call this direction up the incline positive. In the perpendicular direction, I'll go this as positive. That doesn't really matter so much. All right, so now we're going to write out Newton's second law in each direction. And I will start in the perpendicular direction, so I'll start in this direction here. So we've got net force in the perpendicular direction equals ma perpendicular. Now, having said all that, what is that number, or what do I plug in there? Well, what's the block's acceleration this way? Well, hopefully you notice the block ain't moving this way, right? The block's moving up the ramp. The block doesn't have any acceleration this way. This is why we split things up into parallel and perpendicular to the motion. The net force perpendicular to the motion will be a big fat 0 because there is no acceleration that way. So that's 0, okay? All right, now we said this way is positive, so that turns into Fn minus mg cosine theta equals 0, or Fn equals mg cosine theta. Another note, the normal force Fn does not equal mg, okay? The only time the normal force equals mg is if you have something that has no vertical acceleration and there's no vertical forces acting on it besides the normal force in mg. So for instance, this pen, okay, it's not moving, there's no acceleration, and there's no other forces. So in this case, the normal force equals mg. In this case, we got all kinds of stuff going on. The normal force is not going to equal mg. As a matter of fact, here you go. That's what it equals. Okay. Now we'll look at the parallel direction. Okay. That's the more interesting direction. So for that, we've got net force parallel to the motion equals ma parallel. Okay. Well, in the parallel direction, we've got three forces. We got P pointing up, so that's positive. And then both of these guys are pointing down the incline, so they're both negative. So we'll say minus mg sine of theta and minus friction, and that equals ma, okay? Now, I told you we weren't going to need m. Now, right now, it looks like we kind of do because we have two things hanging out here, but we have expressions for those that both involve m. P, I told you at the beginning, that was 2mg. So this is 2mg. We got minus mg sine theta minus, well, what's friction? Well, friction is mu times Fn. Okay. And furthermore, what's Fn equal? Well, we just figured out it equals mg cosine theta. So we got 2mg minus mg sine theta minus mu times normal force is mg cosine theta. That equals ma. Aha! Check it out. I've got an m in every term. Here, 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 and there. So since I've got an m in every term, I'm allowed to cancel out now. Okay, now by the way, you can't cancel it out here. There's not an m in every term. Like if you cancel these two m's out right now, you are doing very bad math, okay? It's got to be in every term in order for you to cancel out. All right, so then I have to do a little math here. 2 times g, which is 9.8, minus g, which is 9.8, sine of 35. Okay, minus mu, which is given as 0.3, times g, which is 9.8, cosine of 35 equals a. And when I plug those all into my calculator, I get a equals, pretty big number, 11.3 meters per second per second. Now you can double check me on that, make sure I got that right. So that's pretty big acceleration, but remember how hard we're pushing. We're pushing with something, a big force. That's twice the sled's, or twice the box's weight. So that's a pretty big force, so you would expect a pretty big acceleration. All right, so that is the acceleration that the box has from here to here. Now notice, and this is very important, sketch the situation out, okay, and then point where things are happening. So that acceleration happens from here to here. And I said, hey, you're going to push on it for 3 seconds. So at that point, it's pretty easy to find the other things I asked you for. I asked you for, well, we didn't actually ask for the acceleration, but we need it to get this and this. So to find the velocity at that moment, okay, the velocity final equals v naught plus at, all right? So I'll use that equation there. I'm trying to find the velocity at the 3 second mark. Well, we started at rest, and I gave you an acceleration, and then the time is 3. So the velocity at 3 seconds equals 33.9 meters per second, okay? Finally, well, not finally, but next, what's x? Okay, so you've got a lot of options here to find x. Probably one of the simpler ones would be delta x equals v naught t plus 1/2 AT squared. You've got everything there. V naught is 0. So if you do that, you get 1/2. You've got an a of 11.3, and t was 3, and you got to square the 3, but only the 3. And if you do that, so what do you get? I got 50.9, so you can double check me on that. Meters, that's how far the block gets in that 3 seconds, which, by the way, is pretty good. That's pretty far, okay? Now, other ways you could have done that. You could have used v final squared equals v naught squared plus 2a delta x. You know v naught is 0. You know a is 11.3. You're trying to find delta x, and you had just found v final a moment ago. So you could have used that. One thing to be careful of, if you've got v final, okay, and you try to use delta x equals vt, and so some people will say, oh, I'll just take 33.9 and then my 3 seconds in there. That ain't going to give you 50.9, because this v is v average, okay? That bar ain't there for decoration. That bar means that's the average velocity. Now that's real easy to calculate in this situation. If your starting velocity is 0 and your final velocity is 33.9, what's the average? Well, it's 0 plus 33.9 over 2, which would be, oh, what would that be? 16.95. So that would be your average velocity, and if you took that times 3 seconds, you're going to get about 50.9, give or take, okay, within rounding. So you could do it that way too. So just if you do it that way, just be real careful what you plug in. Okay. Now finally, so we've got this and this off our list. Finally, we want to find d. How far after you let the box go, you're watching it coast away from you, how far away from you does it end up if you stop here? What's d in the picture, okay? So if you let it go, I hope you'll note that the FBD is going to change now. The only change that's going to happen is, well, you ain't pushing it anymore, so that force goes away, okay? So I'm not going to redraw the FBD, but just note that this is it, okay? These are the 4 forces acting, okay? Up is still positive. That's important here. All right, so if I do that, if I do the net force in the parallel direction equals ma, I'm going to find the new parallel acceleration. It's not going to be 11.3 anymore, okay? Because now it's different forces or different amount of force acting on the box. The net force will be, well, again, P is gone, okay? But these two are still there, and they're both in the negative direction. So I write negative mg sine of theta minus friction equals ma, okay? And so we got negative mg sine of theta minus friction is mu Fn equals ma. I'm roughly following the steps I did before. We got negative mg sine of theta minus mu, and Fn is mg cosine theta, and that equals ma. At this point, now that you've got an m in every term, you are allowed to cancel it. There it goes, okay? And you get, you got numbers for everything else, so you got negative 9.8 sine of 35 minus mu, which was 0.3 times 9.8 cosine of 35 equals A. And if you do that, you're going to get A, and I did it in my calculator, and I got, of course, a negative number, negative 8.03 meters per second per second. So that was my new acceleration. Now, notice that, well, one, it's negative, and that's because, hey, the block's moving up the hill, but it's slowing down. Okay, so the net force is opposite the motion, so you get a negative acceleration. Now, to find how far it goes, I'll use V final squared equals V naught squared plus 2A delta x. When the sled coasts up the hill, we are looking at the motion from here to here. That's V naught, and that's V final. Well, V naught, I know. I calculated that before. We got 33.9. So the velocity there is 33.9. What's the velocity when it gets to the top? Well, we're looking for the max height, which means it's going to stop. That's where it stops. So V final is 0. Okay. So I know this is 0. I know this is 33.9. I know this is negative 8.03. I can find delta x. Now, real quick, delta x, that's our d in that picture. So I'm going to put that in. So I've got 0 equals V naught squared plus 2a times d. If I solve this for d, okay, I move the V naught squared over here, it becomes negative V naught squared divided by 2a. So d will be negative V naught squared over 2a, which is negative of V naught, which is our 33.9 squared. Now, by the way, the negative sign is outside of that, so it's still a negative value, over 2, and then negative 8.03, that's our a. Notice you got a negative in the top and the bottom of the fraction. They cancel out, and you get a distance of, and when I plug those into my calculator, I got 71.6. So 71.6 meters. That's how far the sled coasts from the moment you let it go. All right, so there's a fairly involved problem. A couple helpful hints. Spend a moment or two sketching it out. That's absolutely critical. If you sketch it out and label on the picture the things you're trying to find and where you're trying to find them, that helps an awful lot. Carefully draw the FBD. First, draw the forces that act on it, identify them, and then break them down into components that are parallel to and perpendicular to the motion. And then you write out Newton's second law and solve for whatever they happen to be asking you to solve for in that particular situation. So I hope that was helpful, and thank you very much.